Hey everybody! For my master thesis I was tasked with building a test setup for laser ablation research. In this video I will show you what laser ablation is, what design choices I had to make, how I performed my tests, and what problems were solved during testing. Let's get into it. Laser ablation is a machining process that relies on high-intensity laser pulses in the nanosecond range. These high-intensity, short laser pulses ionize the molecules by knocking off electrons with minimal heat introduction to the base material. By performing the ablation process underwater, the plasma can be better contained and more material is removed per pulse. A laser pulse is traveling through the water, hits the base material and forms a plasma. The plasma heats up the water around it and creates a rapidly expanding vapor layer. This rapid expansion also creates a shockwave. The vapor layer expands into a cavitation bubble. The cavitation bubble implodes after its initial expansion, sending out a second shockwave. After the second shockwave, persistent bubbles are formed which can last for several seconds. This is a long time considering the pulse frequency of an ablation laser starts at a few kilohertz. The persistent bubbles can obstruct the laser from reaching its intended destination by refracting the laser light. In the image here you can see there was an attempt to ablate straight lines, but due to the persistent bubbles this was not possible. A solution to this problem is introducing a water flow to remove the bubbles. There are several setups that are presented in the scientific literature already. There are setups with turbulent flow and laminar flow. But the nicest flow is a fully developed flow. The nice thing of a fully developed flow is that the velocity profile of the fluid is known. Knowing the velocity profile can greatly enhance the understanding of the interaction of the flowing fluid with the ablation process. The design of the test setup will revolve around creating a channel which can facilitate a fully developed flow. The plasma, cavitation bubble, shockwave and persistent bubbles can be imaged using a shadowgraphy setup. Any of these ablation phenomena can obstruct the light coming from the lead on the left of the channel, leaving a shadow on the camera lens. I considered two options for the construction of the glass where the laser shoots through. A round glass which can be mounted in a threaded insert such that it can be screwed in the channel. And a rectangular glass, which can be glued in place. The round glass is more easily mounted, but the rectangular glass has a higher transparent area. For that reason I went with the rectangular design. If we look at the side view of the velocity profile of the fully developed flow in a rectangular cross-section, we see a parabolic shape. This parabolic shape is typical for fully developed flows. When we pan to the top view we can see a section of the profile that doesn't change over the width of the channel. That is a consequence of the width of the channel. When we increase the size of the laser glass, the size of the 2D flow is increased. With the 2D flow I mean that the parabolic shape doesn't change with the width of the channel. For the final design I choose the 25 mm wide laser glass. This gives me a 2D section of flow where the laser spot location is not that critical. The ablation phenomena will experience the same velocity profile even if there is some error. I also considered the optical access. The ablation phenomena can be very small, but the design allows access for a lens with 50 times magnification and still be at the edge of the 2D flow section. The channel is designed to 700 mm long. This length is needed in order to let the flow fully develop. At the beginning of the channel, the velocity profile can be considered a plug flow. But as the fluid travels through the channel it develops into a parabolic shape. To create the liquid flow I used a hydraulic cylinder. The cylinder is driven with a linear motor made by Linmot. The Linmot is connected to the cylinder via a wire flexure to circumvent any misalignment errors. The Linmot is a great motor with precise position and speed control. This is useful for creating a constant volumetric flow rate without pressure variations, which would be present with a centrifugal pump. The hydraulic cylinder needed to be replaced since it started leaking. It was replaced with a pneumatic cylinder since that was readily available. For each test multiple craters have to be shot at different locations on the sample. So, the sample has to be moved relative to the laser. Two ways to move the sample are moving the entire channel and mounting the camera and lead fixed relative to the laser, or rotating the sample and mounting the camera and lead to the channel. The latter option is preferred as the camera and lead cannot accidentally clash with the channel during the homing procedure of the X and Y stage which the channel is mounted to. To rotate the sample in the channel, I designed this mechanism. The sample is mounted on the driving axle which is axially constrained by the ball bearing. The ball bearing is fixed to the knob which allows the adjustment in height of the sample. The sample needs to be adjusted in height so that it is flush with the channel to prevent turbulence around the sample. The driving axle can be driven with a stepper motor. Now the design of the channel is finalized, we can move on to the flow measurements. I verified the theoretical velocity profile using a particle image velocimetry test, PIV for short. PIV works by taking two pictures with a certain time interval. The velocity of a single particle can then be determined by the distance traveled in that time interval. If a lot of these tiny, passive traces are released in the flow, the entire velocity profile can be mapped. A 2D PIV measurement requires a light sheet such that the particles that are not in the camera's focus do not light up. The shutter speed of the camera should also be set fast enough in order to prevent motion blur. These 2 points are very important to create clear pictures such that the particles can be identified and tracked by the software. The channel is mounted to a big aluminium tube. To that tube an aluminium extrusion profile, with the camera and lead, is mounted. In this way the camera and lead positions stay fixed relative to the channel, even when moving the setup around. At the end of the channel is a buffer tank in which the water flows when it is pushed out the cylinder. At the return stroke the water can flow back into the cylinder. Here is a picture of the actual setup. This is an image sequence taken with a pixel fly camera with 7.3 frames per second. If I highlight a few particles, you can see that the ones in the middle travel much faster. This is exactly what we could expect based on the parabolic velocity profile. Now I can use PIV Lab to analyze these pictures. The result of this analysis is a 2D vector field. From this 2D vector field I can extract the streamwise velocity profile, which, as you can see, is a nice parabola. If I plot the center maximums of an entire test in the graph on the left, we can see that there is some peak in the velocity starting from frame 44. This peak closely matches the theoretical expected profile. The fluid not only requires a certain distance to fully develop, the hydraulic entrance length LH, but it also requires time to fully develop. If you look at a certain point in the channel and let time progress, you can see that flow develops into a parabola after the hydraulic entrance length. I call the frames where the flow is fully developed, steady. The frames of the steady part are merged. The velocity profiles of the steady part of a single flow speed are collected. Then, all the profiles of a certain flow speed are added together and are averaged. If we then compare the normalized test results of Reynolds 1953 and of a higher flow speed, Reynolds 4558, then we can see that the flow did not develop into a parabola. In other words, the flow cannot fully develop anymore. I call the difference between the measured velocity profile and expected velocity profile, delta U. If I plot delta U for all the flow speeds, we get something like this. The black line is delta U and the gray band is the standard deviation from the average. Here we can see that around a Reynolds number of 2000 the flow cannot fully develop anymore. That is because the channel isn't long enough and the laminar flow start to transition into a turbulent flow from this point on. With more tests and better test condition, the test results could have been improved. I expect the optimized test results to look something like this. A clear transition from fully developed flow to undeveloped flow at Reynolds 2000. I also tested the non-centered velocity profile to verify if there is a 2D section of the flow. Here, the test results also suggest that the velocity profile follows the theoretical prediction. Now the velocity profiles have been verified, the test setup can be integrated on the optical table for the laser tests. For the laser test, I removed the line light. I added the shadowgraphy LED and added the stepper motor to rotate the sample. I mounted the whole thing on the X and Y stage on the optical table. The laser will be coming via the Galvo scanner via some mirrors on the optical table. Here you see a picture of the actual test setup. The dashed red line indicates the path of the laser. The final goal of my master thesis is to integrate all these components into a single system that can take picture of the ablation events. In this overview you can see all the components that are needed for a test. The workstation computer, in the top right, is used to control the laser and the X and Y stage. The trigger box is used to sync the LED and camera with the laser pulses. A photodiode picks up some of the laser light and counts the pulses. After 25 pulses the camera is triggered and 5.6 microseconds later the LED is triggered as well. In that way the camera and LED fire at the same time. The Arduino is used to control the stepper motor for the sample rotation. The Arduino also sends a command to the workstation computer when the flow is fully developed. During a test the following things happen in sequence. The Linmot is set into motion and triggers the Arduino when the flow is fully developed. Then the workstation turns on the laser. After 25 pulses the trigger box sends a trigger signal to the LED and camera. The image is exported. Then the workstation sends a command to rotate the sample. Then the cycle repeats. But before we get to the first test, there were some issues to be resolved. The laser glass started leaking due to the PIV measurements at high flow rates. The water on top of the laser glass can distort the incoming laser light. That needs to be prevented. I 3D printed a nozzle to suck away the water on top of the glass with a vacuum cleaner, which worked nicely to circumvent the problem. The second issue was that there still seemed to be some PIV particles in the fluid. To get rid of these particles I used a filtration system that pumped the water through a micron filter. However, this did not seem to solve the problem. It seemed that the particles are bubbles instead, which are probably introduced by a badly vented pneumatic cylinder. As I was running out of time for my thesis, I proceeded with the laser test anyway to make sure the test system works. Here are the test results of the laser test. First we see the images of the laser test in stagnant water. Here we see that the systems of the test setup worked correctly as persistent and cavitation bubbles have been imaged. They are indicated by the red circles. The bright area at the bottom is some artifact of the laser light. The shadowgraphy LED was set a little bit too bright, causing some of the detail to be fade away by overexposure. When we look at the images of the test with flowing water, we see that more bubbles are introduced by the cylinder. The size and frequency of the bubbles increase at even higher flow rates. These bubbles make it very hard to see what bubbles are the persistent bubbles. A way around this problem is using a high-speed camera to dynamically track the bubbles. Or, of course, to get rid of all the bubbles by using a good cylinder. Even though scientific research at this stage was not quite possible, the build of the test setup was successful. The theoretical flow profile was verified with a PIV measurement and the setup was successfully integrated in the laser system. I had a lot of fun with this project and really enjoyed the collaboration with the staff here at the university. For more details about this project I would like to refer you to my master thesis. There is a link in the description down below.